they are atoms of the same element with same atomic number or number of protons, but different number of neutron or mass number. Today we are beginning on relative atomic mass. Relative atomic mass. Relative atomic mass. Now relative atomic mass is what we are beginning on today. Atoms are so tiny. We know that atom, from the definition of an atom, that atom is the smallest particle of an element that can take part in a chemical reaction. Now atoms are so tiny. So that atoms are so tiny that their masses cannot be measured on a balance or a scale directly. We cannot weigh an atom. So because we cannot weigh an atom, we have a way where we can determine the mass of an atom. That's why here we have relative atomic mass. Hydrogen is considered to be the lightest of the atoms. It's considered to be the lightest known element. Hydrogen is considered to be the lightest. Hydrogen is considered to be the lightest element. Hydrogen atom is the lightest element. Hydrogen atom is therefore the lightest. Originally, the mass of hydrogen, now before we were using hydrogen to determine the mass of other elements. Now here we're saying that originally the mass of hydrogen atom was taken as the standard reference atom, the mass of hydrogen. Its atomic mass was arbitrarily fixed as 1 unit. Now the hydrogen was the one being used now because its mass was 1, where hydrogen has a mass of 1. The mass of other elements was found by comparing its mass with that of hydrogen. Now to find the mass of other elements, you are comparing the mass of hydrogen to them. The mass of other elements was found by comparing its mass with that of hydrogen. Now the hydrogen was the standard where was being used earlier on. The idea was to find out how many times the atom of another element is as heavier as that one atom of hydrogen, hence relative atomic mass. Now the idea was just to know how many times is it heavier than that of hydrogen. How many times is it heavier than that of hydrogen? So that's the reason as to why we term it as the relative atomic mass. You are just to find how many times is that element heavier compared to that of hydrogen. Now the relative atomic mass has the symbol of A with a subscript of R. A with a subscript of R. Now with the symbol relative atomic, this now the symbol of relative atomic mass with A and then subscript R. Now this can be expressed mathematically. The relative atomic mass can be expressed mathematically as follows. can be expressed mathematically as follows. Remember, we'll be calculating relative atomic mass. We'll be calculating the relative atomic mass. We'll be calculating the relative atomic mass of different elements. Now, to calculate the relative atomic mass of different elements, this is now the formula we will be using mathematically. Relative atomic mass will be mass of one atom of the element that you want to know the mass, divided by the mass of one atom of hydrogen. So this was the formula that we are using before. For instance, when you wanted to calculate the mass of oxygen that has a mass of 16, remember the mass number is 16. This means that one oxygen is 16 times heavier than that of hydrogen. Is 16 times heavier than that of hydrogen. So, for instance, an oxygen atom has a mass of 16. So this means that it is 16 times heavier than that of hydrogen. Is 16 times that of hydrogen. Sometimes the symbol AR is used. The symbol of calculating relative atomic mass is used together with the symbol of the element that we want to calculate. Now, together with the symbol together with the symbol of the element that we want to calculate in parentheses. So we can have the relative atomic mass of oxygen, which means relative atomic mass of oxygen, AR. Then in parentheses we have O, where O is the symbol of oxygen. This means that we are calculating the relative atomic mass of oxygen. Many changes have occurred, but because many changes have occurred since the scale of hydrogen, since the hydrogen scale was introduced. Now we have changes that have occurred. Many changes have occurred since the hydrogen scale was introduced. Many changes have occurred since the scale of hydrogen was introduced. Since the scale of hydrogen was introduced. Now in the 20th century, the hydrogen scale was replaced by oxygen as the standard, since oxygen combines with most elements. Now, later on in 20th century, the hydrogen scale was again replaced by oxygen, because oxygen is able, because oxygen as the hydrogen that was being used as the standard one was replaced by oxygen as the standard, since oxygen combines with most elements. So it was seen that since oxygen is able to combine with many elements, it was now the one that was being used. But later the oxygen scale was found to be unsatisfactory, because the oxygen has several isotopes, which would have different masses depending on which oxygen isotope was being considered. Now, because of the many isotopes of oxygen, it was unsatisfactory. Now in 1961, the International Union of Pure and Applied Chemistry, that's a UPAC, recommended as the standard the most abundant of carbon isotopes, carbon 12. Now in 1961 they came up with carbon now being used as the standard. Now in 1961 it was recommended that they use oxygen. They use carbon, sorry. They use carbon atom with the carbon with the mass number of 12. Now carbon 12 was the one that was being used for that case, for the calculation of relative atomic mass, where the abundance of this carbon 12 is 98.9. Now nowadays the atomic mass of an element measured by comparing it with the other mass of one atom of carbon 12. Now this is the one that has been taken until today. We are still using it, that we are comparing the mass of the other element to that one atom of carbon 12. To that of carbon 12. We are comparing that of carbon 12. One atom of carbon 12 isotope is going to have a mass of 12 units. Now it is considered to have a mass of 12 units. Is considered to have a mass of 12 units. Now the relative atomic mass of an element. Now because this is the mass of one atom of the element of one atom of oxygen of the carbon isotope, it is taken to have a mass of 12. Now 1/12 of the carbon of the atom of one carbon, 1/12 of the mass of one atom of carbon will be 1/12 multiplied by 12 to have 1 unit. Now to get the mass, so now 1/12 of the mass of one atom of carbon will be 1 unit. Now to calculate the relative atomic mass of an element, this is the formula now we use. This is the formula now we use. This is the formula now in use at the moment. The relative atomic mass of an element will be average mass of one atom of the element over 1/12 mass of one atom of carbon 12. The relative atomic mass. Now let's define the relative atomic mass. Relative atomic mass of an element. Relative atomic mass of an element is the average mass of one atom of the element compared with the mass of one atom of carbon 12. Now the relative atomic mass of an element, will define it as the average mass of one atom of the element compared with one of the mass of one atom of carbon 12. Now this is the definition of relative atomic mass. Relative atomic mass of an element is defined as the average mass of one atom of the element compared with the mass of one atom of carbon 12. Now we have to note that the relative atomic mass has no unit. Relative atomic mass has no unit. Relative atomic mass has no unit. So after its calculation, no unit, we don't indicate any unit after the calculation. So note the relative atomic mass has no unit. It's a ratio of two masses. The relative atomic masses are not whole numbers like mass numbers. This is because the abundance of isotope of an element is different. The abundance is different. Now let's have examples. Now let's look at examples on the calculation of relative atomic mass. Let's now go ahead to see calculation of relative atomic mass. To see calculation of relative atomic mass. To see how we can calculate relative atomic mass of any given element. Calculation of relative atomic mass. Example 1. Let's have here an example. A sample of chlorine is a mixture of two isotopes. A sample of chlorine is a mixture of two isotopes. We have chlorine 35 and chlorine 37 in the ratio of 3 to 1 respectively. In the ratio of 3 to 1 respectively. So that's the ratio. That's the example that we have. That's the example that we have here. That a sample of chlorine is a mixture of two isotopes, chlorine 35 and chlorine 37, in the ratio of 3 to 1 respectively. Now we want to calculate the relative atomic mass of this given chlorine. Now solution. Let's look at the solution now for this. Now solution. Suppose the sample contains 4 atoms of chlorine in the ratio 3 to 1 respectively. Then 3 atoms will each have a mass of 35 and 1 atom will have a mass of 37. So we are saying that suppose the sample contains 4 atoms. Suppose the sample contains 4 atoms of chlorine in the ratio 3 to 1 respectively. Then 3 atoms will each have a mass of 35 and 1 atom will have a mass of 37. The total mass of chlorine 35 will be 35 multiplied by 3. It will be 35 multiplied by 3. That's for chlorine 35. Now, total mass of chlorine 35 will be 35 multiplied by 3. Then while the total mass of chlorine 37 will be 37 multiplied by 1. 37 multiplied by 1. It will be 37 multiplied by 1. Now, therefore, the average mass of chlorine will be, we say that the formula for calculation, total mass of all atoms over total number of atoms. Because now here we have one that has 35 and another one that has 37. Now we are multiplying we are multiplying 35 by 3, then added to 37 multiplied by 1. Then we are dividing by total number of atoms, which is 4, to have our relative atomic mass as 35. Our relative atomic mass as 35.5. 35.5. The relative atomic mass will be 35.5. That will be our relative atomic mass. We have to note that the relative atomic mass has no unit. It is not the mass number, since it is not the atomic number. It is not the mass number since chlorine has two mass numbers 37 and 35. Relative atomic mass is also nearer to the mass number of more abundant isotope. Now, the relative atomic mass has no unit. Relative atomic mass has no unit. Relative atomic mass has no unit. It is the number, it is the mass number, since it is not the mass number. It is not the mass number. Since chlorine has two mass numbers, which is 35 and 37, the relative atomic mass is also nearer to the number of more abundant isotope. Now, when you look here, we can see that the abundant isotope is chlorine 30 with mass number of 35, because it has 3 atoms. It has 3 atoms compared to the 37 that has 1 atom. Now here, the relative atomic mass will be around 35. When you look at what we got here, it is 35.5. Now becomes our relative atomic mass. Let's look at another example. We can see that the abundance of atoms can either be given in percentages, in ratios, or in fractions. Now the first one we have seen, it is in ratios. Let's look another example that is given in percentages. Example 2 now. Example 2, you are given percentage abundance now. So silicon with the atomic number 14 consists of 3 isotopes. That's silicon 28 that has abundance of 92.2%, silicon 29 that has abundance of 4.7, and silicon 30 that has abundance of 3.1. Find the relative atomic mass of silicon. Find the relative atomic mass of silicon. Now we are saying that our example 2, we are given in percentages. That silicon with the atomic number 14 consists of 3 isotopes. That's silicon 28 that has a percentage of 92.2%, and silicon 27 that has a percentage of 4.7%, silicon 30 that has a percentage of 3.1. Now the question is, find the relative atomic mass of silicon. Now solution. Let's look at the solution for this. The percentage abundance simply means that if we have 100 atoms of the element called silicon, 92 will each have a mass of 28. 92.2 will have a mass of 28. Then we have 92.2 atoms will have each a mass of 28. Then you have 4.7 will have each a mass of will have a mass of 29, and finally 3.1 atoms will have a mass of 30. Will have a mass of 30. Now that's the percentage that we are given the percentage abundance. So we are saying that the percentage abundance simply means that if we have 100 atoms of an element called silicon, 92.2 atoms will each have a mass of 28. 92.2 will have a mass of 28. 4.7 will have a mass of 29, and 3.1 will have a mass of 30. Now, therefore, the total mass of this will be, now for the first one, the total mass will be 28 multiplied by 92.2, then we are dividing it by 100. Dividing it by 100. For the second one, it will be because it has mass of 29. Now the total mass will be, because you have 4.7 atoms, this will be the calculation how we'll go about it. Now we'll have the third one that has mass of 30. It will be 30 multiplied by 3.1 divided by 100. Now the average mass of silicon atom is total mass of all atoms. Now it will be the total mass of all atoms. So this is how it will be while calculating it. Then therefore, their relative atomic mass of silicon will be 28.1. We can just predict where the mass will fall around. We can just predict, because the most abundant isotope with the most abundancy, that's where it will fall. Now we have here 28.1. We have 28.1. Now that's the relative atomic mass. That is the relative atomic mass for silicon. Now let's look at the third example, where abundance is given in fractions. The question says, a sample of an element X consists of 9 over 10 of the element is X with mass number of 16, atomic number 8. 1 over 10 of the isotope is 18. The X isotope has 18 mass number and 8 atomic number. Show that relative atomic mass of X will be 16.2. Now here we are already given the atomic mass, but they want us just to show that will be the mass number. That will be the mass number. Now the question is that we show that will be the relative atomic mass. Now solution, it will be they want us just to show the calculation how we can arrive to that 16.2. Now we'll have a formula. Relative mass equals to, remember here we are dealing with the fractions. Now relative atomic mass will be, because the mass number for the first isotope of X is 16, it will be 16 multiplied by 9 over 10. Then we add to the second one is 18, it will be 18 multiplied by 1/10, because the abundance of the second one is 1/10. Because the first one is the most abundant one with 9/10, so we can say that the relative atomic mass will be around 16. That's when we calculate, we get 16.2. Now that's the relative atomic mass, and how we can calculate the relative atomic mass. That's how we can calculate relative atomic mass. Now next thing, let's look at periodic table. Let us look at periodic table. Let's look at periodic table. Let's look at the periodic table. The periodic table, you have learned about the structure of the atom and how the electrons are arranged in various energy levels. We are now going to use that knowledge to build up the periodic table. So we are saying that we have learned about the structure of the atom and how electrons are arranged. So we are going to use that knowledge to build up the periodic table. Have learned the structure of the atom and how the electrons are arranged in various energy levels. Now we are going to use that knowledge to build up the periodic table. The periodic table is organized as a big grid. In the grid, there are rows and columns. In the grid, there are rows and columns. There are rows and columns. So we are saying that the periodic table is organized as a big grid, and in the grid there are rows and columns. The periodic table has rows and columns too. They each mean something different. The elements are placed in specific columns because of the way they behave. They have similar chemical properties because they have same number of electrons in their outermost energy level. In a periodic table, each of the column is called, each is called group. Each of the column is called group. Each of the columns is called group. Each of the column is called group. So we are saying that the periodic table has rows and columns, and they each mean something different. The elements are placed in specific columns because of the way they behave. They have similar chemical properties because they have same number of electrons in their outermost energy level. And in a periodic table, each of the column is called group. Now, the characteristic that the thing that is common with elements in the same column or in the same group is that they have same number of electrons in the outermost energy level. They have same number of electrons in the outermost energy level. Now let's look at the diagram. Let's look at this diagram. Let's look at this diagram now. We can see this diagram. Now these ones are columns that are running from top to bottom. We call them columns. And we are saying that each of the column, we call them groups. Now we are saying that elements are placed in specific column because of the way they behave, and we are saying that they have similar chemical properties because they have same number of electrons in their outermost energy level. In their outermost energy level. In the outermost energy level. Now, elements which are located in the same row or period, elements which are located in the same row have something in common. Now, the rows in this becomes the period. All the elements in a period have the same number of energy levels. If we want to know in which period to find an element, we count the number of energy levels. If it has 4 energy levels, it is in the 4th period. Every element in the top row, the first period, has 1 energy level. All of the elements in the second row or second period, they have 2 energy level. The maximum number of energy level is 7, representing period 7. But for the case of the first 20 elements, we only have up to the 4th row or the 4th period. The periodic table has a special name for its column, where we say that columns are called groups. The elements in a group have the same number of electrons in the outermost energy level. They have same number of electrons in the outermost energy level. So we are seeing that elements are located in the same row or period. Now the rows in the periodic table, we are calling them period, and they have something in common. All the elements in a period have the same number of energy level. So we are saying that if we want to find the period in which an element is, we just count the number of energy levels that element has. Now let's look at a table showing the periods in. Now these are the period. Have the first period here, the second period, the third period, the fourth period, the fifth, the sixth. Now these are the period in a periodic table. Now while naming this periodic table, we just use the numerical numbers. The periods, we use the numerical numbers. But when we are indicating the number of the group, we indicate using Roman number. That should be taken into care. So like when you are asking which group is an element found, indicate that group using the Roman number. And while being asked about the period, indicate that period using the numerical number. That is very, very important. That is very important. Now, an element in the first column belongs to group 1. It has 1 electron in its outer energy level. Because it is in group 1. In its outermost energy level. An element in the second column is in group 2. It has 2 electrons in the outermost energy level. As we keep counting the group, we know how many electrons are in the outermost energy level. Therefore, the group number also is the number of electrons in the outermost energy level. Once you know the group number, that means that you know the electrons in the outermost energy level. That will mean that we know the elements in the outermost energy level. So an element in the first column belongs to group 1. It has 1 electron in its outermost energy level. An element in the second column is in group 2. It has 2 electrons in the outermost energy level. As we keep counting the groups, we are saying that we know how many electrons are in the outermost energy level. Therefore, the group number also is the number of electrons in the outermost energy level. Now, let's look at electron arrangement. Let's look at electron arrangement and how it can help us in indicating an element in the periodic table. Remember, we can be given an element, then we are asked to indicate it where it is found in the periodic table. Now, the electron arrangement. Given the atomic number of an element, we can write the electron arrangement or the electron configuration. We shall illustrate this in the following. As we continue, we shall be illustrating it. The atomic numbers. Now, this is an example here we have. This is an example here that we want to tackle. Now, given the atomic number of an element, we can write the electron arrangement in shorthand. The atomic number of X, Y, and Z are, now this is an example, 12, 13, and 17 respectively. Write the electron arrangement of each. You can pause the video and try it out if you are in a position to write the electron configuration or the electron arrangement of these elements X, Y, Z, given the atomic number as 12, 13, and 17 respectively. Now we have the solution here. Because X has 12 electrons, and remember we said that the first energy level carries a maximum of 2, the second carries a maximum of 8, the third carries also a maximum of 8. Now, 2 electrons in the first energy level, 8 electrons in the second energy level, that will be a total of 10, remaining 2 in the third energy level. For Y, it will be 2 in the first energy level, 8 in the second energy level, then remaining 3 in the third energy level. For Z, it will be 2 in the first energy level, 8 in the second energy level, and the remaining 7 in the third energy level. Now, this is the solution that we have for the 3 elements that we are given here. Now, the X will be 2, 8, 2, Y will be 2, 8, 3, and then Z will be 2, 8, 7. All these 3 elements are in period 3 because each has 3 energy levels. Then X is in group 2 because it has 2 electrons in the outermost energy level. Y is in group 3, has 3 electrons in the outermost energy level. Z is in group 7. Because all this because of the outermost energy level. It is all because of the outermost energy level. Now, the outermost energy level tells us the group that they are in. All these 3 elements are in period 3. Each has 3 energy levels. Now, X, you're saying, is in group 2, Y is in group 3, and Z is in group 7, following the number of electrons in their outermost energy level. Now the energy levels will tell, the number of energy levels will help us to know the period that the electron is in, and the outermost energy level, the electrons in the outermost energy level will help us to know the group that is in, the group that it is in. Now that becomes simple even when we are given even when we are given the periodic table, we can be able to tell which element is where, in which group and in which period, the group and the period. Now here we have our periodic table. Here you have our periodic table for the first 20 elements. Remember we say the first row is period 1, the second is period 2, third is period 3, fourth is period 4. The first column is group 1, the first column is group 1, second is group 2, group 3 third, group 4 fourth, group 5 fifth, group 6 sixth, group 7 seventh, then you have group 8, the column 8. Now those elements in group 1 have 1 electron in the outermost energy level. Those in group 2 have 2 electrons in the outermost energy level. Those in group 3 have 3 electrons in the outermost energy level. Those in group 4 have 4 electrons in the outermost energy level. Those in group 5 have 5 electrons in the outermost energy level. Those in group 6 have 6 electrons in the outermost energy level. Those in group 7 have 7 electrons in the outermost energy level. And those in group 8 have 8 electrons in the outermost energy level, with an exemption of helium that has 2 electrons in the outermost energy level. Remember, helium has only 2 electrons. And because the 2 electrons are in the first energy level, where the energy level of helium is now carrying the maximum number of electrons. It's now carrying the maximum number of electrons. Now it is stable. We will find that in group 8 we have elements that are stable. When you look those in group 8, they are stable. Now checking in the periodic table of elements, we place hydrogen in the first group, in group 1, and helium we are placing it in group 8. Reason being, hydrogen here can be placed in the group 1 because it has 1 electron in the outermost energy level. Hydrogen also can be placed in group 7 because it only requires 1 electron to form to be complete, to be stable. It only requires 1 electron to be stable. When you look at those elements in group 7, they only require 1 electron for the outermost energy level to reach the maximum. That's why you are saying that also hydrogen